Ophir offers a range of measurement solutions for laser power, energy, as well as beam position and size. Together with the appropriate sensors, we offer standalone meters, which can also connect to a PC, as well as PC interfaces. The PC software application that's used to communicate with and control the instruments when they're connected to a PC is our StarLab application. StarLab communicates with the instruments via a USB interface, or in the case of the Quasar, a Bluetooth interface. For instruments that connect to a PC via RS-232, one would use the StarCom application instead of StarLab. We'll now begin with the first steps, and we'll see the basic functions that can be performed with the StarLab software. First, we double-click on the StarLab icon, and we first come to the Select Devices dialog window. Here we see the instruments that are connected and the sensors that are working with each instrument. We'll begin by selecting a single-channel device connected to a photodiode-based power sensor. Open session. Here we see the main measurement screen. It consists of a numerical display, a graphical display, and the left and top control panels. Measurement parameters of the sensor first need to be set from the left control panel. We click on the small plus icon, and we see here the parameters that are relevant to the particular type of sensor that's now being used. In this case, it's a photodiode-based PD300 UV sensor. Here we select whether we're going to be measuring power or single-shot energy for those sensors for whom that is relevant. In the case of a photodiode-based PD300 type sensor, that is not active. We select the wavelength, the range, and because this type of sensor has a removable filter, here we select whether the filter is in or out. Any changes that we make in the sensor measurement parameters are automatically saved into the sensor's memory. Let's look at the readout area. We first have a numerical display. Here we see the power reading, in this case in microwatts, and statistical information about the measurement that has taken place up until now. The minimum and maximum values measured, their average, standard deviation, and the number of times we've been over range, if any. If we wish, we can focus our attention on the numerical readout by hiding the left control panel and by maximizing the numerical readout to fill the screen. This might be useful, for example, if we're working across the room and wish to see the reading. We can maximize the size of the readout even further by hiding the statistical information. If perhaps we're standing a little bit off-center, and because of the reduced contrast of the LCD screen, we find it difficult to see the readout, we can go to this icon here, which quite intuitively suggests toggling between light and dark. When we click on that icon, we indeed do toggle the display between positive and negative, so that even if we're off-center and the contrast is low, we can still see what we need to see. Now let's look at the graphical readout. The time axis of the graphical readout is controlled from outside the graph in this area here. First, for convenience, we'll reduce the time frame so that one full screen takes 1 minute. This is so that things will be moving a little bit more quickly. The values on the y-axis of the graphical readout, which in this case, of course, are the power reading, we can control in a number of ways. We can move the sliders up and down so that we can position the graph conveniently in the center, or we can manually type in a number to set the top and bottom values of the graph as we need to, in this window and in this window. We have various graph types that are available, each represented by an icon. Right now we're looking at a line graph. We could change that to a histogram or a pulse chart. Those are not really relevant for a CW power reading, but they would certainly be relevant if we're measuring a pulsed beam using an energy sensor. We could also use a virtual analog needle. We'll go back to the line graph. We of course need to make sure that we're using the appropriate units. We would set those from here based on the measurements that we see are actually taking place looking at the statistical information. The particular configuration of parameters that need to be set and units that need to be set vary from sensor type to sensor type. For example, if we were using a pyroelectric energy sensor, we would also be prompted to set the maximum pulse width, the threshold energy level, and so on. There are a number of advanced functions that we'll briefly look at. If we go into the options top menu item, in advanced functions we have zeroing. This is to zero the instrument and remove electrical biases that tend to build up over time. We typically recommend doing this every other month or so. Calibrate is to enable advanced users to adjust the internally stored calibration values that have been programmed in during the calibration of the sensor. Again, this is only for advanced users. Channel information tells us the identity of the instrument and the sensor that are now connected. We will now look at the additional functions that are available. StarLab offers a range of functions that make it possible for us not only to get a reading, but also to perform various types of additional processing on the reading. Those functions are accessible by clicking on the functions icon, and the functions dialog window then opens up. As we mentioned previously, the range of functions that are available depend on the type of sensor being used. In this case, we're looking at a photodiode-based power sensor, and the functions that are available are appropriate to that sensor type. The averaging function allows us to smooth out the readings that are being displayed in situations where the power is unstable and the readings are jumpy and difficult to work with or record. When we open up that menu, we're offered a number of different possible time frames over which to carry out the averaging, and StarLab will display not the moment-to-moment power, but a running average of the power averaged over the selected time period. Offset allows us to eliminate a DC background level by setting the power level that's being measured in the background at that particular moment. That becomes the reference value, which will then be subtracted from all subsequent readings. We can deactivate that by moving the slide switch back to the original position. Scale factor. If we're measuring power after some attenuation, perhaps after a filter or a beam splitter, we can enter the attenuation value of that component into here, into the scale factor window, and StarLab will then display for us the calculated power before that attenuation. In many applications, this is useful. For example, if we have a beam coming out of a laser and passing through a number of optical components, we're accessing the beam perhaps after some beam splitter, but we want to display the power coming out of the laser itself. This is how we would do so. dBm is for those applications where we wish to display power in units of dBm rather than watts. For example, fiber optic telecom applications and similar. Normalize. In an application such as where we're measuring the power coming out of a laser, and then after a number of different stages in an optical setup, we could take a measurement, set that as our reference value, and then all subsequent measurements will be displayed as a unitless ratio relative to the reference value that was measured. Density. If we need to display not the total power in watts, but rather the power per unit area, for example, watts per square centimeter, we use the density function. We input to StarLab the dimensions of the beam. If it's rectangular, we're prompted to input 2 dimensions. If it's round, we're prompted to input the diameter. And then StarLab will take the power measurement and calculate for us the power density in units, in this case of microwatts per square centimeter. Again, deselecting that brings us back to an absolute power reading. We will now see how to measure energy per pulse of a repetitively pulsed beam using pyroelectric sensors. From StarLab's Select Devices dialog, we will select the pulsar that has connected to it a pyroelectric sensor, in this case a PE50 BFC sensor. Open session. We now see the main measurement screen consisting of a numerical readout window, a graphical readout window, and the left control panel. In order to set the measurement parameters of the sensor, we first go to the left control panel, and here we're prompted to select whether we're measuring in energy per pulse mode or average power mode, which pyrosensors are able to do. Here we select the wavelength, the energy range. If this were the type of pyroelectric sensor that had a removable diffuser, we'd also be prompted to select whether the diffuser is in or out. Since that's not the case, that particular item is not active. We're prompted to select the maximum pulse width. In this case, because we're using a pulsar instrument, there are two maximum pulse width settings available. If we were using one of the instruments, Nova 2, Vega, Starlight, or the Juno PC interface, we would have 5 different settings available for selection for the maximum pulse width. External trigger is a function that's specifically available with the pulsar and not with the other instruments. This enables us to connect a clock pulse coming out from the laser driver into the pulsar, and that enables us to either detect missing pulses or to trigger some external circuit when a pulse is detected. We will be looking at this more closely in a later segment. We will now look at the graphical display area. We select the units as relevant based on what we know that we're measuring by looking at the statistical information. In this case, we'll leave it at millijoules. Right now, we're using a pulse chart. We have a number of different graph types available, and each of them is represented by an appropriate icon. If we wish, we could turn that into a line graph if that were relevant, a histogram if we wish to express this as statistical information, or a virtual analog needle. We'll leave this as a pulse chart. We can control the y-axis, meaning by either adjusting these manual sliders up and down so that our pulses are comfortably in the middle of the screen, or we could manually type in a number to set the top and bottom values of the y-axis as we require. We can adjust the time axis by the time frame controls that are over here. As we saw earlier, the time axis is controlled from outside the graph. The values on the y-axis are controlled from inside the graph. It's worth noting that the different sensor types are each represented visually by their own icon. In this case, we're using a pyroelectric sensor that's represented by a pyro icon. This will become important when we're looking momentarily at using multiple channels. We'll now look at some of the additional functions that are available to perform various types of processing on the readings. As we mentioned previously, the range of functions that are available depend on the sensor type that's being used. We're offered those functions that are relevant for the type of measurement that's taking place. In this case, if our readings are jumpy and we want to smooth it out, we can select average, in which case StarLab will display the average energy averaged over a selected time period. Scale factor. If we're measuring after some attenuation or similar optical component, a beam splitter perhaps, a filter, we can manually enter the attenuation factor, and StarLab will display the calculated energy or power before that optical component. In some applications, that's helpful. Normalize enables us to take an energy reading and set that reading as a reference value. While the normalize function is active, all subsequent readings will be displayed as a unitless ratio relative to the reference measurement. Density, if we wish to display not energy in units of joules, but energy density in joules per square centimeter, we would select that. For other sensor types, as I mentioned, other functions would become available. There are some advanced functions that it's worth noting. Zeroing the instrument, which we recommend doing periodically, every other month or so, is done here. Advanced users can make adjustments to the internally stored calibration factors of the sensor by using this function. Trigger configuration, we'll be looking at that in a separate segment. That is how we set up StarLab to detect missing pulses or perform other functions making use of the external trigger, which is a capability that the pulsar instrument has. Turbo mode is a mode for when we're doing logging. It enables the maximum pulse rate in instruments that are otherwise limited in their pulse rates. And channel info tells us information about the instrument and the sensor that are currently connected. We will now have a look at logging recorded measurement data. StarLab enables us to record measured data for further analysis or even just for record keeping. We first need to set up the log parameters. We can do this either through the logging menu on the top control panel or through the log control icon over here. The large red button intuitively reminds one of a record button. Before we begin to record the data, we first notice the tool icon. This is the log settings control area. When we click on that, we're presented with a number of options. The default option is to record one screen of data, which in this case is 1 minute of data. That's the time frame that was set on the graphical display. If we deselect that, we're presented with other options: stop after a particular time or stop after a particular number of readings. We'll remain with the logging one screen of data. By clicking on Browse, we can select where StarLab will place the recorded file. If we wish, we can use this icon, Log Notes, to record free text as an annotation in a recorded log file. For example, experiment number 1, June 18th, etc. We can begin the log by pressing on the red button. If we wish, we can stop at any time. We notice that the timing is being shown to us during the course of the logging. We'll now press stop. The stop only refers to the logging process. The graphical measurement continues unaffected. We can now open the logged file by clicking on the file name, and that opens up the file in a file viewer, which is in the same format as the measurement screen itself. Of course, we cannot adjust measurement parameters of the sensor because this is a measurement that has already taken place. But we can adjust how it's being displayed. We can adjust the y-axis, etc. If there were any noted annotations, that text would appear here. When we X that out, we leave the log viewer and go back to the main measurement screen. We can also click on this arrow and go to log file location. Here we see all recorded data files that are found in the library on the PC where we placed them. And we can open them either in the same log viewer format, or we can open them as text. When we open them as text, what we see is in notepad form, basic information about the measurement that took place, the settings that were in use, statistical information, and the recorded measured data points themselves, each with its timestamp. We can also open the file using Excel or export it to other software applications as our application may require. Beginning with StarLab version 3.10, it will be possible to upload instrument files from onboard our Vega or Nova 2, etc. By going to the logging top menu, and that function will be available in the list. We will now look at how to use multiple channels simultaneously. One of the capabilities that StarLab 3 has is the ability to add channels on the fly without having to shut and restart the application. We have one channel already operating. We can now add another channel either by clicking on that Select Devices icon or by going to the Select Devices top menu. Because it's so intuitive and pretty clear what the intent of this icon is, we'll do it from here. We click on that plus, and we're taken to the Select Devices dialog window. In addition to the PD300 that's already connected, we will now select the pulsar, which has a pyroelectric sensor connected to it, and open session. We could merge the two channels onto one graph. For convenience, we'll keep them separated by clicking on Split. The time axis is common to both or all channels. The y-axis values are independent of each other and are controlled individually from within the graph. Each channel is represented both by a color scheme, they're color-coded, and also there's an icon that represents each sensor type, not on a resolution of individual models, but here, at least intuitively, even from a distance, we can see that this is the channel that has the photodiode sensor working with it, and this is the channel to which a pyroelectric sensor is connected. As we saw previously, the y-axis values can be controlled individually from within the graphs, either by using the manual sliders or by manually typing in the appropriate values at the top and bottom of the y-axis. Graph types are represented by appropriate icons. There's the line graph. If we wish, we could change that, as we saw previously, to a histogram, a pulse chart, virtual analog needle. We need to make sure that our units are appropriate, as we saw previously. And we can add a number of channels. Usually we define the maximum as about 7 or 8, but in principle one could go higher. Clearly more than 4 windows would not be very useful in terms of an operator seeing what one is doing. One can perform data logging with multiple channels simultaneously, and all channels will appear in the log file, both in the log viewer format and in the text format or exported to Excel. We can also add what we call a math channel. When we click on the function button, we open up a new channel. The previous channels were labeled A, B, C, etc. The math channels begin with M, and we can add subsequent math channels which will then be named N, O, P, etc. The math channel is treated as an additional sensor operating in parallel to the other sensors for all practical purposes, and we can define this math channel in pretty much any way we need. We have some typical functions. For example, this math channel M can represent the ratio of A over B, or A plus B, etc. Or if we don't need to use any of those default favorite functions, we can define our own using free text. And we can manually type in pretty much any function that our application requires, and it will be displayed on a graph and logged if we so require. As with any other channel, we can X that out and get rid of it or bring it back. When using a pyroelectric energy sensor together with the pulsar instrument, we can configure StarLab to detect missing pulses. Here's the basic idea. If we have a sync pulse, but no matching laser pulse is detected by the sensor, we can set up StarLab to record a missing pulse. Conversely, if the sensor detects a laser pulse, but we have no matching sync pulse, we can have StarLab ignore the detected laser pulse and assume it to have been spurious or noise. To illustrate this, consider this diagram. Here are the sync pulses. Let's say we configure StarLab to look for the rising edge of the sync pulse. We can tell StarLab to expect a laser pulse during some defined time window before and after the sync pulse's rising edge. If no laser pulse is detected by the sensor during this time window, StarLab records a missing pulse. We can also have StarLab ignore any detected laser pulse that's outside this time window, if that's what our application needs it to do. This is done as follows. First, we need to take a clock output from the laser driver and connect it to the BNC connector on the pulsar instrument. We then need to turn the external trigger function to on. Once that's done, we go into the options top menu item and go into advanced functions. We select trigger configuration. Here's where we're going to actually tell StarLab what to do. By selecting the appropriate trigger configuration mode, we can tell StarLab to look out for the rising edge or the falling edge of the clock pulse. And then we can configure StarLab to only pay attention, for example, to pulses that come within a specific time window before and after the rising edge or the falling edge. We would enter the appropriate time frame here. We can also configure StarLab only to pay attention to pulses that come while that input is held high or held low. We're also able to configure StarLab to send out a pulse from that BNC connector anytime a laser pulse is detected. This can be used, for example, to trigger some external circuit. Here we would configure StarLab to send out a pulse that's either high or low by selecting output high, output low from the trigger configuration mode. Please feel free to visit the Ophir Photonics Group website for further information or to download the latest version of the StarLab application.